Hi, I'm presenting VIP Bench, which is a benchmark for evaluating privacy-enhanced computation frameworks. I'm presenting today with Lauren Biernacki, and I want to acknowledge my colleagues at University of Michigan, Addis Ababa University, and New York University. And I also want to acknowledge our sponsors, the Ada Center at Michigan, and SRC and DARPA. So let's take a look at why we need privacy-enhanced computation frameworks. And it really stems from the fact that data security is not very secure today. We see breaches everywhere. And that's really for two reasons. One, endless software vulnerabilities. These are bugs in software, and bugs are created when people write code, and people are writing loads and loads of code. This graph here shows you the number of lines of code that are executing in a Boeing Blue or Airbus commercial airline when it takes off, when wheels leave the ground. And it's literally 50, 60, 70 million lines of code, doubling every 4 years. How do you find and fix all the vulnerabilities in this framework? Well, you don't. You attempt to using inspection, and then you use formal tools, and they don't scale to this size of a program. And ultimately, you have the realization that all software is hackable all the time because you can't fix all the vulnerabilities. So if software is protecting your data is always at risk. Second, even if you could fix all those vulnerabilities in your software, you still have side channels everywhere in software and in hardware. These are observable properties of the system that reveal secrets about the underlying system. They happen because of control flow in programs, how you access memory, the timing of operations, how you access the cache, how you speculate. Just a great example is Spectre and Meltdown from 2018, how these very clever attacks use multiple side channels in the system and really pervasively hit all of the systems in the industry. Really difficult to stop vulnerabilities. So people are going to get access to your data. And the reason why I really love PECs, privacy enhanced computation frameworks, is because they don't try to fix software. They try to build a wall of crypto between software and the data it accesses. And that is really a better, more pragmatic approach. So instead of operating, on X for f of X, which is Y, the result, we operate on encrypted X, apply the function f, and we get encrypted Y. What's interesting about this is now the programmers can use their proprietary algorithms to direct the computation, but they themselves cannot see the inputs and they cannot see the outputs of the computation. Software is denied access to that data. And so if someone hacks into your program, all they get to see is ciphertext. The hacks are essentially broken. Even though the vulnerabilities exist, there's nothing to steal but ciphertext. Really powerful technologies. Two I really want to highlight here are homomorphic encryption and multi-party computation. So now Lauren Biernacki, the lead PhD student on this project, she's going to introduce the VIP bench.
Are you tired of shopping for privacy technologies? As a customer that cares about data privacy, you are faced with seemingly endless options. From hardware techniques like trusted execution environments to cryptographic methodologies like homomorphic encryption schemes, the coverage of these technologies vary widely, and so do the costs. But choosing a technology that best suits your performance security trade-offs is difficult, as making comparisons between these options is seemingly impossible. These products can use confusing messaging and often compare overheads against non-native baselines. These differences in measurements make it impossible to compare two competing products directly. So how do you choose? Don't you wish you could compare privacy technologies more easily? Don't you wish you could be treated like a VIP? Well, now you can at VIP Bench Market. Here at VIP Bench Market, all of our products are tested against a uniform set of benchmarks. These results are printed clearly on the product packaging as performance overheads over a native baseline. These performance facts are organized by operation complexity and computation depth, enabling customers to easily compare the performance costs of two competing technologies along the axes that best match their application needs. These performance labels are generated by our custom benchmark suite, VIP Bench. VIP Bench provides a flexible interface to support the varying programming constraints imposed by different privacy technologies. Furthermore, VIP Bench contains workloads designed with privacy applications in mind, including genomic algorithms, orbital collision detection, and elementary cryptography. These workloads can be separately enabled depending on the interface supported by the privacy technology. For example, data-dependent conditionals cannot be readily expressed using Microsoft Seal's CKKS homomorphic encryption scheme, making search and sort operations difficult to support. Our breakdown by operations and computation depth allows for evaluations on a subset of the benchmark suite to support even the most restricted designs. Once this computation is complete, VIP Bench outputs performance facts that make it easy to compare competing privacy technologies. We are especially interested in evaluating your own privacy technologies, as VIP Bench enables easy comparisons against native execution, as well as cutting-edge commercial privacy technologies like homomorphic encryption. Overall, at VIP Bench Market, you can shop with peace of mind and easy evaluation of performance security trade-offs using our novel benchmark suite. We hope to see you try out VIP Bench soon. Thanks for watching.
Thanks, Lauren. So as she mentioned, the VIP Bench really facilitates PEC comparisons. And this was really driven by our study of the literature of PEC frameworks. They tend to look at the performance of privacy enhanced computation framework X and compare it to the optimized version of that same framework. Rarely do you find anyone comparing the native execution or any other framework. And if we want to continue to mature and grow this field, we really need to start truly assessing the costs of these frameworks, driving those costs down, and then competing against each other in terms of what we can deliver. So we can produce the very best frameworks that can essentially deliver the promise, the tremendous promise that they have. So VIP Bench facilitates this comparison between native and competing PECs, and it provides comparisons in the form of performance, memory use, execution capabilities, and security analysis. It does this with three primary components: the computational model, which defines how these programs execute private computation, and a reference implementation that performs that using Intel's AES-NI instructions. It provides a number of benchmarks that are built for that particular computation model. And then it provides interfaces to the system to allow you to easily port this framework to your privacy enhanced computation model, and also to port new benchmarks into the framework. So let's take a look at the VIP computational model, which is really a stretch goal for PEC frameworks. Nobody really implements everything we've got here. The goal is really to put something out there that's a bit ahead of the community, and maybe we can reach that point. Because once we can reach that point, we can execute some very interesting codes. It assumes that your PEC framework supports C++ with encrypted variables, and the operators of C++ operate on those encrypted variables, either in a scalar or in a SIMD form. And so we provide access to a number of operators, from linear arithmetic to nonlinear, relationals, booleans, casting between floating point and non-floating point, even conditional execution operators. And we've arranged them in this way because certain frameworks provide access to all these or more of these, and others, such as homomorphic encryption, typically only support linear arithmetic. So we've tried to build benchmarks that have varying gradations of these operator needs. So if you don't support all these, there's certainly some benchmarks you can still run in this framework. In addition, the computational model enforces what's called data oblivious execution, which basically means that you can't do if conditions on encrypted variables, can't control the program can't be influenced by secrets, and you can't generate an address to memory that in part of that address computation there was any secrets in the program, because otherwise you'd build easily exploited software side channels. So this is not allowed. Now, fortunately, the computational model provides some facilities to help port normal programs, which do this all the time, into this framework. For example, there's a private conditional move operation that allows you to say convert this if statement here that counts even and odds into this data oblivious predicated 2C moves, for example. And then for accessing memory, we have some private information retrieval techniques that you can utilize so that the memory access is not reflective of the secrets. The benchmark suite is arranged based first in terms of the degree of operational complexity. There's certain benchmarks that have low complexity, just linear operators, and then other benchmarks that require conditionals and nonlinears and Booleans, etc. And then we also arrange the computation, the different benchmarks by the depth of the computation. And this is reflective of some PEC frameworks that utilize noise as a protective mechanism. And so the deeper your computation becomes, the more likely you have to do an expensive operation to reset that noise, or maybe you can't even go past to those deep computations. So, if you are a low complexity, shallow PEC, you can execute these benchmarks in this quadrant here. But really, as a community, we really want to go to the deep end of the pool over here and really start to execute these high operational complexity, deep computations. In terms of evaluating benchmarks, in terms for the VIP benchmarks, we've got a lot of facilities. At the very beginning, you've got just how many of these benchmarks can you execute, right? If you can do deep computation with high complexity operators, then you can run them all. Maybe you can't run them all. That's an interesting point of comparison. Second, what is the performance of your PEC framework in executing these benchmarks? We do this on a per task basis, so it's a fixed amount of work. How quickly can you do it? What's your wall clock time? What's your instruction counts? And we compare that to native execution, which is unencrypted best algorithm, and then data oblivious, which is unencrypted and a blind algorithm. They can't look at data. So you can compare native to data oblivious to see what is the cost of my algorithm for not being able to see the data that I'm operating on. And then finally, you can run your full PEC framework. And if there's other PEC frameworks that execute that benchmark, you compare head to head on a per task basis. In terms of memory requirements, we look at peak and working set size of the benchmarks. And then upstream, we've got some initial security analysis work. And at this point, we're focused on doing what's called indistinguishability analysis, where we take random samples of ciphertext from the privatized program running in the PEC framework, and then we analyze that ciphertext to see if it looks like true random data. If it doesn't look like true random data, there's some information there, and that's a concern. Everybody should be able to pass this in the very least. So please come take a look at our paper and go to this bit.ly link here and check out our pre-release of the benchmark suite today. And we look forward to working together with the community to continue to push forward these really incredibly exciting PEC technologies. Thank you so much.